Differentiable 3D Gaussian splatting is emerging as a popular technique. Gaussian splatting uses explicit scene representation as a set of 3D Gaussians and employs a computationally efficient splatting operation. Given images captured from multiple views, the parameters of 3D Gaussians can be trained and stored. The neural representation can learn XY information when capturing in the front and YZ information when capturing from the side. However, in the restricted baseline scenario, such as scanning the seafloor or a room, it will overfit on the training dataset. This is called missing cone problem. Let's consider 2D volume, assuming no interreflections and far-field sensing, which is like the volumetric scene after the local affine approximation in the Gaussian splatting algorithm. The rendered RGB image corresponds to the X splatting of the volume. The Fourier domain of this image is equivalent to the X slice of the Fourier domain. By capturing multiple images from various angles, we obtain different slices of the Fourier domain. However, in scenarios with small baselines, we encounter the missing cone problem, which refers to a cone in the Fourier domain that is not sensed by the camera. To address this issue, we propose to fuse time-resolved measurements, particularly those from sonar. These measurements can be obtained by taking the z-axis splatting of the volume, which I will explain in a second. This is equivalent to obtain a z-slice of the Fourier domain. Thus, sonar data can help capturing the missing cone in the limited baselines. In practice, we have a scene represented by the Gaussian. As mentioned in previous papers, the scene can be transformed to an orthogonal wheel with a local affine approximation. Note that after the transformation, the value of the Gaussian kernel is the Euclidean distance from the Gaussian center to the camera. This preserves the physical accuracy in our z-splat model. For each ray in the image frame, if there are Gaussian along the ray, we splat the Gaussian on the xy plane as well as the z-axis, resulting in a 1D Gaussian distribution along the z-axis. Note that if a Gaussian is blocking multiple rays, it will be splatted multiple times. Therefore, we can get similar results no matter there are multiple small Gaussians or one big Gaussian. Besides, if one Gaussian is occluded by another one, the intensity will be multiplied by the transmission. After completing all the iterations, we obtain an intensity distribution along the z-axis, which can be used to fit the sonar intensity distribution. We combine our technique with two different types of sonar. The first one is a simple echo sounder. There is a speaker emitting pulse and a receiver, which is a microphone. When the sound bounces back, we can decode the pulse and get a 1D intensity signal which shows the echo intensity with respect to the distance. The second one is forward-looking sonar. Compared to the echo sounder, the FLS does not only give a resolution of depth, but also gives a resolution of azimuth in the circular sector. Here is our fusion pipeline. First, we follow the original Gaussian splatting, which is XY splatting. In the simulation and emulation process, we start from a depth map with pixel as resolution. To simulate the echo sounder, we histogram the depth of all the pixels to obtain an intensity distribution corresponding to depth. Note that in hardware experiment, the intensity distribution is directly calculated by the meshed filtering algorithm. Finally, instead of splatting on the xy plane, we splat Gaussians on the z-axis to obtain a predicted depth intensity distribution. Both distributions are normalized and used to calculate the depth loss. For FLS splatting process, instead of histogramming all the pixels, we histogram per row to simulate the azimuth resolution that FLS gives us. Additionally, we splat Gaussians on the YZ plane to obtain the predicted FLS result. We first show the simulation result. Our proposed methods successfully minimize the occurrence of floaters and produce high-quality novel views, as shown in the blue dashed boxes. We observe an average improvement about 6 dB in PSNR compared to RGB-only algorithm, with 10 dB increase in challenging scenes that contain little texture. We also increase 5% in SSIM and have 40% less in LPIPs. We also conduct tests on the geometry between the reconstructed point cloud and the ground truth. To visualize the differences, we generate a set of scenes with only one object. In the corresponding figure, we display the ground truth as a mesh and the Gaussians as a point cloud. It is evident that the RGB-only method have more errors along the z-axis, as indicated by the dashed boxes. To quantify the results, we calculate the chamfer distance and F1 score between two point clouds. Here is a quick recap. First, we iteratively choose a point from one point cloud, and then we find the point in another point cloud that is closest to this point. We average the distance of all the point pairs for the chamfer distance and calculate the matrix based on the threshold for F1 score. Finally, we change the order of 2 point clouds and get the final result by combining them. Here's our quantitative result. Our methods are 46% less in chamfer distance and also have constantly higher precision, recall, and F1 score in both room scenes and one objective scenes. For emulation, we made a Cornell box and captured the RGB image along with their corresponding depth images. The novel view images rendered by our algorithm are sharper and clear, especially while there has low contrast. Besides, with multiple runs using different random seeds, our methods stay constantly, while RGB only can get much worse in some cases. We outperform RGB-only method by 5 dB in PSNR with higher SSIM and lower LFP scores. Additionally, as I said, we quantify the stability by conducting 10 training runs using different random seeds. Our methods exhibit lower variance and superior performance. Omka and Suren from ASU have set up echo sounder hardware with camera, speaker, and microphone. They capture the scenes on the attending table and do the corresponding experiment. Again, we have a better reconstruction quality in the novel scenes than RGB only. With the turning table, we also do a baseline analysis. We rotate the circular table by various ranges of angle and compare the geometry reconstructions. As we expected, the missing cone becomes narrower as the baseline increases. Hence, we only have a diminishing gain from the sonar. We also show the visual reconstruction comparisons. It is clear to see that our method has less Gaussian kernels, which will result in faster rendering, and we have less error on z-axis. Mohamed, Kevin, and their PIs also help set up the forward-looking sonar hardware to do the corresponding experiment. Our proposed fusion method has significant less error in the z-axis than RGB only, as shown in the red dashed box. We decrease the chamfer distance by 40% and increase the F1 score by 12%. Here's the conclusion. We present a novel forward model to render the transient of Gaussian point clouds for two types of sonars, echo sounder and forward-looking sonar. We propose fusion algorithm for camera and sonar. With the validation on synthetic emulated hardware and real hardware datasets, we show that the fusion Gaussian splatting results in better geometric and photometric reconstruction than standard camera-only Gaussian splatting. Some of our collaborators also propose a similar project called EONews. The goal for both EONews and this Splat is to fuse acoustic and optic data with neural representations. EONews is based on neural surface so that we have different forward model. This Splat is about 10 times faster than Aeonius, taking the advantage of splatting operation. Finally, we admit that the Aeonius geometry reconstruction are slightly better than us. Aeonius is accepted and will be presented at SIGGRAPH 2024. If you happen to be in Denver next week, we highly recommend you check it out. Thank you for listening.